everybody. So this will be the last one of these. We're coming to the end of the semester. Um, this is going to be like the last video where I'm going to do a lecture at the beginning, and then the second part is going to show you how to do your fourth assignment and final assignment. Both are going to include correlation, which is actually really simple. In all honesty, I still think the hardest assignment of all semester is the second assignment. You should have finished the third assignment at this point. As you know, that's not terribly difficult. This is, at least in terms of doing correlation, in my opinion, is an easier analysis to run. And also it is the case that it's really quick. I mean, you're really only running two continuous variables to see the association that they have with one another. And then you can really quickly interpret what that is. It's really straightforward to interpret. Pearson correlation, which is what we're going to do. So yeah, we'll go and get started. The only change in this video is I decided that you should see my smiling face. Like I said, I'll just run through the lecture slides that I have here. As was the case with the other lecture slides, I'll post everything that I have. But also I'll kind of mark what is not relevant for you. It was always my intention for you guys this semester to be doing less abstract math by hand than was the case for my previous semester, but given that we're online, the entire semester has been thrown for a loop, it's the case that you are done at this point with doing math by hand. How to do Pearson correlation by hand is included in these slides. You won't have to do it for the final exam. I just want to give it to you so you know what it looks like, so you kind of know what the nuts and bolts of the equations are, but it is by no means necessary for you to know for the final exam. So when you see all the big scary equations, and in all honesty, for Pearson correlation, the equation gets really big and really scary. Like, chill. You don't need to worry about that stuff. So I am just going to kind of tell you what the Pearson correlation is. After this, I'll show you how to do it in SPSS. Like I said, it's really, really quick, really simple. There's not a whole lot that you need to account for. And ultimately, all you really need is two continuous variables. So what a Pearson correlation is a measure of association. You're taking two continuous variables and you're measuring how much they covary. In other words, how much they go together. And so if it is the case that there is covariance between two variables, when one goes up, the other should either go up or go down. But when one changes, the other should change as well. You'll either have a positive or a negative correlation. If one goes up, the other goes down, thus negative correlation. If one goes up and the other goes up, then you have a positive correlation. So you could do, really any pairing of continuous variables. Income and life expectancy. Naturally, it's the case that in the sociology of health, we know that the higher somebody's income is, the higher somebody's life expectancy is in turn. And so there's a really reliable, strong, positive correlation between those variables in basically any analysis we ever do in the social health. So what you are trying to disprove with the null with Pearson correlation is that there's independence. And you already know this from when we did the chi-square test of independence. But independence is just no association whatsoever. It's the opposite of covariation. And so if it's the case when one variable changes, the other just doesn't change at all, or there's not really enough change to suggest that there's a linkage between the two, then you have independence. And fundamentally, what your null hypothesis is always going to be is that the two variables are independent of one another. And what your alternative hypothesis is going to be, if it's two-tailed, is that there's some sort of relationship, whether it be a positive relationship or a negative relationship. Of course, if you have a one-tail hypothesis, you will have a hypothesis about the direction of that relationship. But fundamentally, if two variables are independent, then the null is true. There's nothing going on between these two variables. So what you will get at the end of doing a Pearson correlation is something called a correlation coefficient. Or it's also called Pearson's R. So what it is a single number that summarizes an association between two variables. It's a number that ranges between 0 and -1 or 0 and +1. So in other words, you will get an answer that is somewhere between -1 and +1, or it could be, near 0. A positive correlation is going to have a positive number, and a negative correlation is going to have a negative number. Now, if it is the case that your variables are independent from one another, then it is going to be the case that you are going to get a Pearson correlation that is near 0. So a +1 indicates there's a perfect positive correlation. So as variable A moves up 1 unit, variable B moves up 1 unit. They move exactly in tandem with one another. A -1 is a perfect negative correlation. As one moves up 1 unit, the other moves down 1 unit in perfect tandem. Now, a 0 means that there is 0 correlation whatsoever between the two variables. Now, it is going to be the case that you're very rarely going to get a perfect 1 or a perfect -1 or dead at 0, because, I mean, there's always randomness in the world. Two variables, even if they are very strongly associated with one another, are almost never going to covary perfectly, either positively or negatively. So what you want to account for is the strength of your correlation that you get, the strength of your Pearson's R, your coefficient. And so anything that is greater than 0.50, or less than -0.50 is a very strong correlation. Anything between 0.30 and 0.49 is a moderate correlation. Anything between 0.10 and 0.29 is a weak correlation. And anything less than 0.10 is very weak or no correlation whatsoever. You just would pretty much keep your null hypothesis at that point. Now, naturally, I mean, these numbers are going to be either positive or negative, depending on, if you have a positive or negative correlation. But this is one of the unique elements of the Pearson correlation. And one of the reasons why continuous variables are the best variables to use is you can actually speak to strength of relationship when it comes to correlation. That's something you couldn't do with any of the previous tests that we've done. And so that is unique. Not only do you have the ability to say that a relationship is significant and reject or keep a null hypothesis, but you actually have the ability to say, like, okay, how strong is this relationship? That wasn't something that you could do with t-tests or chi-square. And so you can do that because of the nature of continuous variables. So once again, this is, how correlation works, positive or negative. This just reiterating the nature of the strength of correlation. Now, it is important to note that a correlation of -25 and positive negative 0.25 and positive 0.25 are equally strong in terms of their strength. They're just in opposite directions. And so do note that. The strength of the correlation is ultimately determined by how far your coefficient is away from 0 and how close it is to 1. If it's very close to 1 and far away from 0, then you're going to have a really, really strong correlation. If it's closer to 0 than 1, then you're going to have a weak correlation, or a correlation that's not even really worth noting. So I'll give you an example, and I think I do have an example here in these slides. That's the association between education and wages, hourly wages. So years of education, hourly wages. Now, if you do the math with this, you can see that there's probably, there is a positive correlation between years of education and hourly wages in this example. But to do a more entertaining example, you could do two continuous variables out of basketball, just because the world of basketball is interesting to me. And so you could look at what is the correlation between the amount of rebounds a basketball player in the NBA gets per game and their height. And so this is how you would do this by hand. You would set up two tables. You have your X variable and your Y variable. And X variable here is height in inches. Y variable is rebounds per 36 minutes of playing time. And you would want to see like how much these things link. So, like I said, you're not going to have to do any of this by hand. Take pity on my fall students because they did do all of this by hand. But you'd use tables to do this. And so this is what the equation ends up looking like. This is what you'll get automatically when you do this in SPSS. Now, like I said, I'm not going to go through the nitty-gritty of how to do this equation because it's not necessary for you this semester. But I do want to show you what the end result is in this example to kind of give you an idea of how to interpret it. And I also want to introduce you to the concept of R squared. So your Pearson correlation equation gives you R, it's your coefficient. And so at the end of all of this math, comparing these numbers right here between height and basketball rebounds per game, we got an R, or correlation coefficient, of 0.80. That's pretty strong. Obviously that is relatively close to 1 on our scale from -1 to 1. And so that's a really strong correlation. And you can also, once you have your R, you can do something called R squared. R squared actually gives you the percentage of variance that one variable accounts for in the other. So, to use the example, this actually makes a lot more sense once it's put into the context of an example. The relationship between basketball player height and rebounds per game, or per 36 minutes, it has an R of 0.80. So we know right off the bat that's a pretty strong correlation. So, and it's positive, so that indicates that it is the case. The taller you are, the more rebounds you grab. Now, you can actually take that number and you can just plug it into your calculator and you can press the squared button and you get R squared, which R squared tells us in this circumstance that 64% of the variance in rebounds is accounted for by height. So what that means is for the NBA basketball players in the data set that I gave, and that's actually all based on real numbers, 64% of them being good rebounders is just merely a function of height. It's not heart, it's not hustle, it's not skill, it's just being tall. And so that is one of the interesting things you can do with a Pearson correlation, is you can say like, okay, like, what does it take to be a good rebounder? How much of it is not necessarily skill or will or determination or talent even, but just being straight up a tall person? And so you can do a Pearson correlation and then just square your R, and what that tells you is exactly how much of your Y variable, how much of your dependent variable is accounted for with your independent variable. And so in this instance, we know that 64% of being a good rebounder is just straight up being tall. And so, yeah, this is, to give you an idea of how we get significance. Now, significance for you will be automatically done in SPSS, so like don't worry about it. But just in case you were curious, which like maybe there's one of you out there that is, it is the case that in order to get significance, you actually can use a t-table to find out what the significance of your r is. You have to convert r to t, which is possible using this equation right here, and then you use a t-table. But at the end of doing this equation, you actually go back to doing your t-tables to find significance. I'm not going to make you do that, so don't worry about that. So that is all. Actually, I'm gonna get rid of this, and I'll give you the slides that I've just gone over here. I actually had a review of t-test, 2-sample t-test for my last semester. I'm just gonna get rid of that altogether. The only other thing I wanted to point out is this is where scatter plots come into play. So fundamentally, in order to visualize a relationship between two continuous variables, a correlation, the best way to do that is a scatter plot. And the reason is you can, just by nature of the scatter plot, tell if there's a positive correlation or a negative correlation, no correlation, and what the strength of that relationship may be. So a strong positive correlation is going to be this strong upward slope like this. Moderate, it's going to be a little bit more scattered, less strong, less coherent, but still, you can see it's a positive correlation. No correlation, there's just no pattern whatsoever. Negative correlation, this downward slope. Strong negative correlation is this really defined downward slope. And then there's actually, maybe if you go into grad school, you can learn about curvilinear relationships and how those are measured. A curvilinear relationship is where a relationship is either positive or negative to a point, and then it changes. But yeah, you don't have to worry about curvilinear relationships this semester. In fact, I doubt that you will have to learn about how to statistically analyze curvilinear relationships unless you're to go to grad school. So the rest of these slides I have here are, I've got the example with wages and years education, where I run through the math of that, which is the same thing I did with the basketball example. Do remember, how to interpret the strength of your correlation and the direction. But yeah, you don't have to worry about doing any of this math. I'll leave it in here just, because it gives you a chance to understand the nuts and bolts and kind of go above and beyond if you really would like to. Yeah, so that is Pearson correlation. Like I said, it's something that's relatively simple. I will go ahead and stop here, and I'll pick this video back up, and we'll look at how to do this in SPSS. And we'll also go over the details of your final assignment. Okay, welcome back, everybody. So let's go over your fourth and final assignment. So I'm going to go ahead and do portions of this. Now, this is actually a fairly substantial revision from last semester. And so this is actually going to be the first time that I've gone through and done this. So you'll get to see any mistakes I make along the way, but I'll be sure to point them out and correct them promptly. So you are going to be using a different data set with this. You are using the American National Election Studies data set. This is a data set that's been collected from a survey that's been done every year since 1948. And you have every survey's results going back to 1948 in this data set. This is a really, really, really thorough data set. This is actually the data set that I just most recently used for the latest publication I have under review. So yeah, you are getting a sense of the kind of data sets that we actually work with in sociology, and this is actually a data set that's not surprisingly more common in political science. But this specifically asks questions that are not only sociologically relevant, but also, given it as a national election data set, politically relevant as well. Now, it is the case that this data set, and given that it's so old, or at least some of the surveys in it are so old, it is imperfect. And there is a flaw in one of the variables that you will actually have to account for and correct. But I will walk you through how to do that. Um, for the first part of the assignment, aside from the basic recoding that you'll be doing, um, you are going to be using what is called feeling thermometers or group thermometers. These are really, really simple continuous variables. It asks somebody on a scale of 0 to 100, how do you feel about this group of people? So, 0 would represent a strong dislike for a group of people. 100 would represent a strong like for a group of people, and 50 would represent absolute indifference for a group of people. So, I mean, that's obviously a really simple continuous ratio variable. We're going to be doing correlations, so you're going to want, a really good continuous variable. Now, you're actually going to be doing a correlation between that and your independent variable, which is going to be the year of the study. So your independent variable, in effect, is time. And so what you'll be doing is you're going to be trying to see if political partisanship, or at least disdain between liberals and conservatives, has grown over time. What I'm going to have you do is use select cases and feeling thermometer variables to look at how liberals have viewed conservatives over time and how conservatives have viewed liberals over time. And you are going to see if it is indeed the case that the two groups have grown to dislike each other more as time has gone on. I mean, that seems to be conventional wisdom. Like I said, I just put together this assignment in some current form, so in all honesty, I don't recall off the top of my head what the answer is coming out of this data set. So, I'll discover that as I go through this, and you'll discover that as you go through this assignment. But do keep in mind that, it is the case that your independent variable in this instance is time, and your dependent variable is going to be that feeling thermometer, either towards liberals or towards conservatives. So yeah, like I said, go ahead and download this data set. It's already on Scholar. You'll write out your hypotheses. And the very first thing that you're going to do is you are going to create a binary variable. And that binary variable is going to identify cases as either liberals or conservatives. Now, this binary variable doesn't exist in the data set from the get-go. This is something that you're going to have to create. And so in order to do that, you're actually going to use the variable for political self-identification. So if you go to, let's see, VCF, and all of the variables have VCF code or name to them. VCF 0803. So let's go all the way down, all the way down, all the way down. 08. Let's see, 0803. Here we go. So this is political ideology. So here's what you have in the original coding for the VCF0803 political ideology variable. You have each case saying whether they are on where they are on a scale from extremely liberal, liberal, slightly liberal, moderate, middle of the road, slightly conservative, conservative, or extremely conservative. And you also have 9. I don't know or haven't thought much about it. And so you also have 0 for NA or no answer. So what you are going to do here is you are going to take this variable and make a new variable. So you're going to code into a different variable that will be a binary variable that either identifies somebody as liberal or conservative. how liberal or conservative, you don't care. Like, that's not part of this analysis. You just want to put them into one of two categories. And so we are going to take VCF 0803, and we're going to transform it and go to recode into different variables. Let's find our variable again. VCF 0803. Now, old and new values. So 1 through 3 is some variety of liberal. And so we are going to code all of our liberals as 1. So you can actually do, rather than enter them one by one, you can do a range. So range 1 through 3, we're going to code them all 1. Now 5 through 7, that's some variety of conservative. We're going to code them all 2. Now, for those who are middle of the road or just straight up moderates, we don't really care about them in our analysis. We're trying to see how liberals feel about conservatives and vice versa. And so in this instance, like, the moderates aren't really relevant to the analysis that we're doing. So we're going to take the 4s and we're just going to system missing. Same thing is going to be the case for our 9s. Like, they can go. So I do know that there's also a 0 code in here. So we'll code that as system missing as well. Like, all we want is liberals and conservatives. So that's it. That's the recoding scheme. We're going to call this, I think, what do I have in here? libcon? Libcon, yeah, we'll call it libcon. Label liberal or conservative. Change. All right, so we have our new variable. Should be down here at the bottom. Let's go ahead and give it value labels. So 1 liberal, 2 conservative. All right, so let us go ahead and just check the frequencies. I like to do this whenever I create a new variable, just to make sure my frequencies make sense on the new variable. So like, if I somehow seriously screwed up the coding, I should get frequencies that like don't even make sense. So, okay, here we go. Looks like we have we've got somewhat more conservatives than the liberals. There's a good chunk of our data set that we sent to missing. So there's a good chunk of our data set that, or 64% of our data set, either didn't answer that question, didn't want to identify ideologically, and did not want to, or they're moderates, or they're true moderates, and they didn't identify as liberal or conservative. That's fine. They don't have to be part of our data set. We will do our analysis just with the liberals and conservatives. But off the bat, it makes sense. So we'll go ahead and assume that this is a good variable. So we've got our binary variable all set up. Now, the next thing that you need to fix is your feeling thermometers. The feeling thermometers you are going to use is feelings towards conservatives and feelings towards liberals. Now, what you're going to do in your analysis is you're going to see how liberals look at conservatives, or how they view conservatives, and how conservatives view liberals, and you're going to do case selection. And that's why it was the case that we made our binary variable we just did, because we're going to use that binary variable in order to do case selection. So I know that I can do case selection on libcon for 1, and I only have liberals in my data set that I'm using. Or I could do it by 2, and I know I only have conservatives. And so that gives us the ability to, look at how each group views each other. So that said, let's go ahead and fix our feeling thermometers. Now, like I said, this is a really old data set. And so given that it's not an old data set. I mean, the data set just came out this past year. This is a very old survey. And so a lot of times is the case that data sets that are based on old surveys that have been done for a long time, they end up having a lot of kind of weird ticks and idiosyncrasies. And sometimes that leads to variables that you need to fix. Um, in the case of this data set, the big problem with the feeling thermometers is they're supposed to be between 0 and 100. They actually go between technically, well, I'll actually just show you. Frequencies. So our first feeling thermometer is VCF0212. So, okay, so I just did what I explicitly told you not to do, which is use frequency distributions for a continuous variable. So this is why, because look, that's a huge frequency distribution, but it actually illustrates what the problem here is. Just because of something finicky with the old survey, all the codes go from 0 up to actually 97. And 97 is the code for anybody who has a response that's between 97 and 100. Why that is the case exactly, I don't know. It probably has something to do with something weird that happened in a survey back in the 1950s. And so we just have to accept that our variable, despite the fact it's supposed to go to 100, actually only goes to 97. And anybody who on the survey fell between 97 and 100 actually gets counted as 97. And so that's just something we're going to have to deal with in our analysis. So 98 is don't know. And 99 is no answer. Somebody didn't post. See, that's a problem. Because if you're to do your analysis and you weren't to fix the fact that 98 and 99 indicate don't know or not applicable or didn't answer, then it's going to treat it as a valid case. And it's going to treat somebody who, let's say you asked the case, like, how do you feel about conservatives? And their response was, I don't know. The code gives them a 98, which a 98 generally indicates extreme like or an extremely favorable view, which totally is going to screw up your data. And so why they coded 98 and 99 for no answer or don't know is beyond me. Is a really dumb thing to do, because obviously if you don't know that it's supposed to end at 97, you assume that a 98 or a 99 is an extremely favorable response, rather than a don't know. In all honesty, this is just a bad job of coding that, in my opinion, they did in this data set. So you're going to need to fix that. So let's go ahead and fix that. This is going to be really, really simple. You are going to go to transform, and you're going to recode into same variables. You can actually knock both of these out of the way at once. So our two feeling thermometer variables is going to be VCF 0211 and VCF 0212. Okay, here they are. So go ahead and put them both in. Old and new values. We know value of 98. That should just be missing. That should not be a valid case. So we're going to treat all those as missing because their answer was, I don't know. So what value are they? Just get rid of them. So 99, no answer. System missing as well. Get rid of it. All right. Recode, here's our syntax. Recode has been executed. Now, one more time, let's do the thing that I tell you never to do. Just to make sure that, look, yeah, it is the case that 98 and 99, they're gone. We threw them all out. Now they're all in this missing category here. So that's good. That's fine. 98 and 99, they don't mean anything to our analysis. They can go. So cool. So this is that's how to set it up. Now, let's go ahead. I'll run one example that it's not exactly what you're going to be doing, but it's very, very similar. So you'll get a different answer, or you'll get a different final result than I'm about to pull up right here. But let's go to the feeling thermometers again. They were in the VCF 02 range. Okay, here they are. We have a bunch of different group thermometers. Let's see. Actually, let's just let's do something with VCF 0214. This is actually the feeling thermometer towards police. So I'm going to do the exact same thing that I did do earlier, and I'm going to recode into so 0214 police, old and new values. Okay, actually, just for a good measure, I'll just do the same thing over again. System missing, 9, system missing. Okay. Okay, cool. So I have fixed the feeling thermometer towards police the same way we did our feeling thermometers towards liberals and conservatives. So what I'm going to do now is I am going to run a correlation. This is super, super simple. So you're going to go to correlate, and you're going to go to oh, actually, no. Let's not do that. I got ahead of myself. We're going to select cases. So what I want to do is I want to see how the feeling thermometer, the relationship between time and the feeling thermometer towards police among liberals. So let's go to select cases. Now we're going to use our libcon variable as select cases if libcon, let's say, equals 1. In other words, the person has identified as a liberal. So it's like most of our cases have been nixed out, with the exception of a few, and those would be the liberals. So we've got our case selection done. So the next thing that we're going to do is we're going to look at the group thermometer and its relationship with time. So we're actually going to go to correlate, bivariate, and now we know our group thermometer that we're using is 0214. So I'm actually almost there already. So, okay. So VCF 0214, that's our thermometer towards police. And let's see, I've got in here the time. Study year, VCF 004. So this should be really easy to find. In fact, it's the very first variable in the data set. So we've got our two continuous variables. Since they're both continuous, like, it really doesn't matter what order you put them in. Make sure you have Pearson correlations selected. Two-tail or one-tail. I would say do all of your tests two-tail at this point. Make sure it says flag significant correlations. That's just going to note when it is the case that your correlation is strong enough that it would be considered statistically significant. So you don't have to break out the old t-test table. This, I'd leave this as is. Exclude cases pairwise. Don't worry about that. Okay, let's run it. All right, so it appears that we have an incredibly weak correlation. Actually, it's weak enough that it's not statistically significant. If you remember, anything that's below 0.10 is a really weak correlation, and this is really weak. So your correlation actually shows up, your correlation coefficient, or your R, actually shows up in two different places. It shows up here and it shows up here. So, I mean, it's doubled because it's, for each variable, it shows how much it's correlated with the other variable, and that correlation is the same for each variable. It notes the significance, and the significant p-value 0.26. It's not significant at, 0.05 level. So yeah, this is not significant. In all honesty, what this is telling us is the relationship between the views of liberals towards police in time, has not changed. Or in other words, liberals have not viewed police more favorably or less favorably throughout time between 1948 or now. So, in fact, there just doesn't seem to be much of a relationship at all. It's been steady. So, I mean, we can, just for fun, we can do the same thing with conservatives just by going back and selecting different cases. So, libcon 1, libcon 2, because I coded conservatives as 2. So now we have all of our conservatives selected. Go back to bivariate correlation. Everything's cool. Now we have a significant correlation. It's positive. So what this is saying is, as time has gone on, conservatives have viewed police more favorably. Now, it's not the strongest of correlations. It's only a correlation of 0.165. It's positive. So it's more favorably over time. As time has gone up in years, the favorability of conservatives towards police has also gone up. So it is significant. And actually, I mean, it's quite significant. It's the case that we have an N of 3,374. We've got a lot of cases. And so having so many cases allows us to have a fairly weak correlation and have it still be statistically significant. With Pearson correlation, like everything else, if you have more cases, the pattern can be lesser in order to meet that standard for statistical significance. And so since we have over 3,000 cases, we almost have 3,400 cases. We can have a kind of weakish positive correlation and still have it flagged here as statistically significant. Statistically significant at the 0.01 level. So it's fairly significant. So it looks like, just by playing around here with the data set, we've found something. We have found a socio-political pattern through time among American voters. So that's how you're going to do that. I mean, you're going to do that. You're going to get different results because you are going to be doing it to see how liberals view conservatives and how conservatives view liberals, rather how liberals and conservatives respectively view police. But you're going to be doing the exact same basic process here. So that's it. For the last part, this is the quote-unquote flying solo part. And so you're not actually going to have me doing this on video because this is all stuff that you've done before. So what I want you to do is write out 2 sets of hypotheses with an alternative for each based on variables you have available to you in this data set. Actually, and I'm going to get rid of the +1 you created to an established variable. I'm not going to have you do any more recoding. I'm going to just let you pick variables from this data set, come up with your own hypotheses, and test it. Now you're going to do 2 different sets of tests to test 2 different hypotheses. Now I want you to choose the appropriate statistical test for the variables that you have. Now, I created a little cheat sheet here to jog your memory in case you can't remember what statistical test is appropriate for what different kinds of variables. Now, I want you to do 2 different statistical tests, so don't just give me 2 chi-squares or 2 t-tests or 2 Pearson correlations. Make a combination and pick 2 of the different ones. And yeah, and test, sincerely, whatever you want. You have so many options here. Now, if you're looking to do something that involves a continuous variable, or well, given you need at least 2 of those 3 tests, you will have a continuous variable in at least one, because you can't do 2 chi-squares. If you want good continuous variable, I'll tell you that these group thermometers, or the feeling thermometers, however you want to put it, these are great. You're going to have to fix the coding on any of them, though. Do the exact same thing you did before. They all have that problem with the 98 and 99. You've got anything you can think of on here. You've got race. You've got political affiliation. How important it is that a candidate is inspiring, knowledgeable, moral, displays leadership, cares, is angry, as afraid. So you can see what appeals to people about candidates, what they like or dislike about the Democratic Party or the Republican Party. You can see feeling thermometer towards specific candidates. Now, do keep in mind, obviously, these were only done at specific years. George, going all the way back to Ted Kennedy, Hubert Humphrey, George McGovern, and Walter Mondale, and Ed Muskie, and all sorts of other names that you surely don't know. But you probably have heard of Ronald Reagan, George Wallace, or well, not, well, George Wallace if you know about civil rights history. Hillary Clinton's on here, Bill Clinton's on here. I don't know where it's at. Trump's on here. This is recent, so I can tell you that views towards Trump are certainly on here. Views towards government assistance with medical care, in urban unrest scale. I don't even know what that means. But seriously, whatever you want to develop a hypotheses for and test, that is up to you. This is the opportunity for you to truly fly solo and apply things that you've already done through this assignment and the previous assignments to answer a question you are curious about. And I'll go ahead and say that is the only requirement for selecting these. I want it to be something that you are legitimately interested in. So anyways, I'll post this assignment. Naturally, I went over superficially all of these requirements, but read each individual bullet point and follow the directions as closely as you can. And in here, like I said, in the flying solo part, where you get a bit of independence, do something you are legitimately interested in. I want you to come up with a question that you legitimately want the answer to, because that is the beauty of statistics. And in all honesty, that's why I do quantitative data analysis rather than qualitative data analysis. Fundamentally, I'm impatient. At the end of the day, I am 2 things. I am curious and impatient. And being a quantitative researcher gives me the ability to get answers to questions instantaneously. And I love that about going through data sets, is you can come up with a question and you can get an answer almost as quickly as you can come up with that question. So, anyways, have some fun with that. Best of luck. Naturally, it is the case that I am available to assist you. If it's the case that you're having troubles with SPSS, we can do a Google Hang or Google Meet, and we can even share screens, so I can see your screen and you can see my screen and vice versa. But best of luck. I hope everybody's staying safe, staying sane. Yeah, best of luck with all of your other classes at the end of the semester. And I will talk to you soon.